Okay, welcome back to part 3 of this tutorial. I just noticed a mistake. I just had a quick review of some of my comments from the last one. Oh man, I made some mistakes in it. For example, I called this the H plus concentration, but anyway, I'm sure you got the picture and you've all moved on, so let's do that same thing ourselves right now. Solid sodium chloride is added to 5 litres of water. The water has got this, where's my pen gone? Has got this concentration of stuff in it. Okay, cool. Calculate the minimum mass. Okay, let's just not even worry about the 5 litres or anything like that first. First of all, we go through and we are going to do the Ks thing. Ks equals the Ag plus, okay, and the Cl minus. Do I know anything there yet? Yes, I do. I know the Ks. Okay, the Ks has been given to me already, and I know the Ag plus. Cool. So that's really, really excellent. All I need to do now is calculate the Cl minus concentration, which is too easy. I'll show you why. Ks, what is it? 1.56 times 10 to the negative 10. 1.56 times 10 to the negative 10. Oh, wait a minute, let's just rearrange that right now before we do anything else. If I go through and rearrange that, it's a times by. On the other side, it will become a divided by. Cool. Equals the Ks divided by the Ag plus. You may be thinking to yourself, but wait a minute, it's in 5 litres. Who cares? Every litre has got 0.1 moles per litre in it. Cool. What am I doing? Oh, that's right. This is the Cl minus, which is the thing we're after. Right, so the Ks was 1.56 times 10 to the negative 10. 1.56 times 10 to the negative 10. Divided by the Ag plus concentration, which is just up there. 0.0100, and that's going to give me 1.56 times 10 to the negative 9, I think it is. No, that's good. I've gone through and made another big mistake. Paching, that's better. Fixed. Okay. So, here we go. That's our number. That's in moles per litre. You may be thinking to yourself, oh cool, I've already gone through and answered everything, haven't I? Well, no. Unfortunately at the moment, I've gone through and I know the amount of chloride moles I've got to add per litre. Okay, so how many moles, if that's that many chloride per litre, then how much NaCl do I add per litre? Exactly the same moles. Why? Because if I'm adding NaCl, I'm adding 1 lot of Na and 1 lot of Cl. If I'm just adding Cl, I'm adding 1 lot of Cl. So in other words, it's all good. That's just fine, exactly how it is. Okay, moles per litre. Cool. But unfortunately, let's go through. Calculate the minimum mass of sodium chloride I have to add, not the minimum amount. That's the moles per litre I've got to add. We've got to work out how many grams per litre. Oh, good thing. They've gone through and told me there is 58.5 grams per mole. So I get that thing there. Now I could use a triangle if I wanted to. Here's a triangle. Okay. Grams, that's a mass per mole, and the big capital M thing there. I could work out the mass by getting the molar mass times the amount, the moles. 1.56 times 10 to the negative 9 moles. Okay, so that's the moles times the molar mass. That one right there. Cool. So times, get my pen out of the way, 58.5 equals Okay, and whoops, I'm still in highlighter mode. And that is going to give me the following mass. Okay, have I done it all right here? Just checking my answers. That's all good. Cool, yes it is right. Equals 9.1 times 10 to the negative 8 grams per litre. Now you probably think to yourself, hey, wait a minute though, you don't have just 1 litre, you've got 5 litres. So I times that by 5 litres, and that's going to end up getting rid of my litres out of there, times 5 equals 4.56 times 10 to the negative 7 grams in total. That's going to be that many grams in 5 litres. Because I had 9.1 times 10 to the negative 8 grams per litre. But because I've got 5 litres, that's all good. Times it by 5. Okay. Discuss the reasons for the fact that the precipitate of silver chloride dissolves on the addition of excess aqueous ammonia. Okay, this is bringing us right back to the aqueous chemistry, not aqueous chemistry, the atomic structure and bonding things we looked at earlier, and the complex ions. Okay, we didn't actually need to know too much about complex ions. It's great if we do. Okay, we just need to basically talk about the fact that either the silver concentration or the chloride concentration is going down. Okay, it's going down. In other words, I'm changing the ionic product, and therefore meaning I put more and more silver or chloride into it. Okay, how's it doing that? Okay, so we have the ammonia and it's reacting with the silver. It's an equilibrium situation because it goes backwards and forwards, and we end up getting this complex ion being formed here. Now remember, back to our earlier stuff on complex ions and a completely different topic. Normally we have these things here, and they normally have 4 of those attaching to the metal. But this is one of those exceptions to the rule. When silver and ammonia get together, there is in fact only 2. And that thing there has a total charge of 1 plus. Let's balance that as well. So 2 lots of 0 and 1 plus make 1 plus at the very, very end. Cool. So we need to say that the ammonia is reacting with the silver, therefore decreasing the silver ion concentration. As I decrease the silver ion concentration, I am increasing the solubility. Actually, no, don't use the solubility. I am increasing the moles. Yeah, I'm increasing solubility. The moles per litre of AgCl that I can dissolve in the solution. Why? Because the silver ions are disappearing. Remember that whole ionic product thing? How I've got Ag plus and the Cl minus. Only when the ionic product is greater than the Ks do we have a precipitate forming. Well, now I'm making this amount of Ag, which was like that big there, it's getting smaller and smaller and smaller. Okay, and therefore I'm increasing the amount more I can put in there. Okay, so checking the answer at the side here, make sure it's all okay. Increase the solubility of the silver chloride, causing more AgCl to dissolve, and therefore the precipitate disappears. Cool, good stuff. Right, moving on down. I need more to go. Yep, I'm going to need one more tutorial after this one. So, question 3. Oh, that's awful. Let's try that. 25 mils of 0.0500 moles per litre of benzoic acid solution, that's the formula right there, is titrated with that much sodium hydroxide solution. Okay, not that much, sorry, that concentration. Cool. The equation for the reaction is this. Beautiful. The titration curve for the reaction is this, and then it says write down the formula for 4 species apart from water and H2O plus that are present at the equivalence point. Okay, equivalence point is about there. Okay, so we need to go through now and write in those horrible chemicals that are present then. Every time we have got H plus present, or H3O plus, I also have OH minus in every situation, never different. So tick. That's a cheating one, but it's all good. Now notice as well, sodium was there as well, so I can put sodium 1 plus there as well. That's all good. Okay, I have been adding the benzoic acid. Notice the sodium's on both sides. It's all good. So I'm going to have C6H5COOH, and I'm also going to have benzoate as well. C6H5COO 1 minus. Okay, cool. That's my 4 species present at the equivalence point. As we go up and down along this titration curve, okay, we get different amounts of it, but those guys will pretty much always be present. Cool. Let's move on down. Explain why the solution in the titration flask has buffering properties after 9.8 mils, okay, so 9.8, so it's right about there, of the NaH solution has been added, but not when 25 mils has been added, so at the equivalence point, in other words. Okay, so why does it have buffering properties through this area from there up to there? Okay, buffers. First of all, let's talk about buffers. What is a buffer? A buffer is a solution that contains a certain amount of the weak acid and its conjugate base. When they are present, I could add more. Okay, this is the acid here. Here's the base here. I could add more and more and more acid, like H plus to it, and something happens. The acid doesn't have the effect on the pH that it should. Okay? In other words, the base here is chewing away at it also. Okay? I could add more and more and more base to it, and then the acid would chew on it. So we're adding these things that should be changing the pH a lot, but we're not getting the same change occurring. Okay, they're able to resist the changes in pH. Okay, now, why does it start buffering after that point there? It's because we had the benzoic acid at the beginning, but we have made benzoate. Okay, we've made benzoate, which is going to have a conversion property going on there. It's going to start converting the extra acid because it reacts with it. It neutralizes it. Okay? But there's still unreacted benzoic acid available. Okay? So, the benzoic acid is still there. And therefore, it is buffering it in the other direction. As I'm making more benzoic acid, because the equilibrium is turning it into benzoate and making more benzoate, that can therefore eat up more of the acid that I'm putting in there. Okay, how to put that into words? I've made benzoate and benzoic acid, still remains. Okay, I'm going to pause this here for a second, and I'll come back to the rest of this tutorial very soon. In the final section, I hope.